This lesson addresses the topic of the antiderivative or indefinite integration. Up to this point in the course, we're familiar with having a function and finding its derivative. This lesson, we're going to be given the derivative, and our task will be to find the original function. Integration is a word that most of us are familiar with. In the dictionary, it's defined as the act of bringing together smaller components into a single system that functions as one. That is the summing of the parts to make one. And I think that's the social definition of integration, but is also precisely what we'll be doing in calculus. The antiderivative could be called the inverse of the derivative. To find the inverse, you do the opposite operation in the reverse order, and we'll see that that's precisely what we'll be doing in this lesson. Let's consider the following. You're given the fact that the derivative of a function, f prime of x, is x cubed, and our task is to find the original function. So if the derivative of the original function is x cubed, then we stands to reason that the original function must have been x to the fourth. So if we assume that f of x equals x to the fourth, let's check and see. Let's take the derivative of x to the fourth. We get 4x cubed, not x cubed. So 4x cubed is not the function that gives us a derivative of x cubed. So let's make an adjustment. Let's assume that f of x were 1/4 x to the fourth and take the derivative. And when we do, we get 1/4 times 4, which is 1x cubed. So we can now assume that 1/4 x to the fourth is the original function. However, consider f of x equals 1/4 x to the fourth plus 8 and find f prime of x. That also gives you x cubed. Or f of x is 1/4 x to the fourth minus 18/7. The derivative negative 18/7 is 0. That also gives you x cubed. And as does f of x equals 1/4 x to the fourth plus the square root of 11. So let's make one more adjustment. We see that f of x equals 1/4 x to the fourth plus any number will satisfy the requirement and have a derivative that is equal to x cubed. Now we could probably work lots of examples. We have here 100 examples. Hopefully, eventually, you would see a pattern. But we're not going to do that. I think just working this one problem is probably sufficient for us to come up with a formula that will give us the antiderivative when we're given x to a power. And so we make this statement: if y prime is x to the nth power, then y must be, that is the original function, must be x to the n plus 1 divided by n plus 1 plus c. In other words, add 1 to the exponent and then divide by that new exponent plus c. This is the power rule for the antiderivative. Now let's look at some notes we have here. Note 1. We do not derive antiderivative formulas. If you recall, working with the derivative, we had to derive the derivative formulas. In particular, the power rule, we used the definition of the derivative, if you recall, and we did quite a bit of work to come up with the derivative of x to a power. But with the antiderivatives, we don't derive the antiderivative formulas. We simply think backwards. Think backwards. Now, one of the nice things, note 2 says, one of the nice things about the antiderivative that we did not have this luxury with the derivative is we can check to see if our answer is right. In other words, when we find the antiderivative, we can immediately turn around, take the derivative of this answer, and see if it gives us our original given. If it does, then we can pretty much assume we are correct. Note 3. We said that the derivative and the antiderivative are inverse actions done in reverse order. Consider the following. If y is x to the 5th and you want to take the derivative, what do? Well, first you multiply by 5, and then you subtract 1 from 5 and get the 4. On the other hand, if you're given the derivative 5x to the 4th and you want to find the antiderivative, the first thing you do is you add 1 to 4 to get the 5, okay? And then you divide by the new exponent, which we do, which gives us the desired answer. So we first, for the derivative, we multiply first. For the antiderivative, we divide second. For the derivative, we subtract second. And for the antiderivative, we add first. And that's what we mean by saying we do the inverse action in reverse order. Okay, so you've got to do some thinking backwards when you're working this. And this really lends to doing a lot of gymnastic work in your head. Before we go further, we need a command for the antiderivative. We have a command real often in mathematics to replace sentences. For example, when you're told find a number when multiplied by itself to give you 16, that's rather wordy. We would like to have a command that says that, and we do. Square root of 16. That when you have the radical over 16, that means find two numbers that multiply themselves to give you 16. And we do this throughout mathematics. We take sentences, verbal sentences, and convert them into sentences with special math notation. So we want to do the same thing here with the antiderivative. Rather than say, if f prime of x is x to the 7th, what is f of x? Let's see if we can come up with a notation that is acceptable. The antiderivative is synonymous with summation. We talked about that when we talked about the word integration, summing, okay? In early mathematics, we used a capital S, was used to represent summation. Over time, as happens often, this evolved into a sort of a lazy S, which you see here, okay? And that's the notation we're going to adopt for the command for finding the antiderivative. So rather than say, if f prime of x is x to the 7th, what is f of x? We'll write the lazy s, x to the 7th dx. And of course, the answer is add 1 to 7 is 8, divide by the new exponent. So we have x to the 8th over 8, or 1/8 x to the 8th plus c as our answer. Now, you must have the dx attached. Just to have the lazy s with x to the 7th means nothing. This indicates, the dx indicates that this represents the derivative of something, and we would like the original. In other words, the expression that gave us this x to the 7th. Okay, so we need that dx. That's necessary. And so we have a note here that states that. In addition, the dx tells us that the x is a variable, and that's not so dramatic here because we only have x as our variable. But if you have an expression, say, in terms of x and y, then The dx indicates that at that part of the problem, x is the variable. If it's dy, it indicates that y is in play. So it's very important. It serves a number of purposes. So you want to write it as the lazy s, your function, dx, or whatever the variable happens to be. Let's look at an example. Probably the easiest way to learn this formula. Evaluate x to the 11th dx. So what do? You add 1 to 11, which we do, over the new exponent, which is 11 plus 1. Of course, 11 plus 1 is 12. 11 plus 1 is 12. And so this is x to the 12th over 12, or we write 1/12 x to the 12th plus c. You must include the plus c. Now, we do not need to see this step, and we will not be putting this in the future. We just wanted to emphasize the fact that you're adding 1 to the exponent and dividing by the new exponent. We do not need to see that. We want you to take it right to the answer, okay? So as we say here in this note, we will not be showing the intermediate step, only the answer. Don't forget the C. That's a part of the answer. Now, the exponents do not have to be a positive integer. They can be any real number except -1, and we will explain that in a bit. Let's look at example 2. Here we have a negative exponent. So you add 1 to -7, it gives you -6, and divide by -6, which is the same as multiplying by 1/6, and there is your answer. Now be careful. You know, we're so used to, when we take the derivative, we subtract 1. When we do the antiderivative, we add 1. And remember that adding 1 to -7 is -6. Be careful there. You can get confused. Okay, so be careful there. Let's look at example 3. Here we have a fractional exponent done the same way. You add 1 to 3/2. Suggestion: write 1 as 2/2. Then add 2/2 plus 3/2 is 5/2. Now you divide by your new exponent. Well, the new exponent is 5/2, but dividing by 5/2 is the same thing as multiplying by 2/5. And so it's 2/5 x to the 5/2 plus c. Try to go straight from the given to the answer. In this case, if you have to show the intermediate step, do. But see if you could get to the point where you add that 2/2 and you get 5/2, and then say divide by 5/2 is multiply by 2/5, and be through with the problem. Example 4. X to the pi power. Pi is a number. Okay, we don't want it as 3.14. We want it as pi. What happens when you add 1 to pi? What do you get? You get pi plus 1, and divide by the new exponent, which is pi plus 1. Okay, or 1 over pi plus 1 times x to the pi plus 1 plus c. Pretty straightforward and seemingly fairly simple to carry out. Now here we have the 5th root of x. So what did we do when we were taking derivatives? The power rules says it's x is to a power. Well, this is not x to a power. So what we've got to do is realize that 5th root means x to the 1/5 power. Now you're ready. Add 1 to 1/5. Think of the 1 as 5/5. Added to 1/5 is 6/5. Divide by 6/5. You invert and multiply. 5/6 x to the 6/5 plus c, or 5/6 x times the 5th root of x plus c, or several ways of leaving the answer. Okay, any of these are good answers. Okay, but make sure you can get to this point. 1 over x to the 8th. Again, x is not to a power, but we can write 1 over x to the 8th is x to the -8, Add 1 to minus 8, makes it a minus 7, divide by minus 7, or minus 1/7 times x to the minus 7. There's an answer, and there is a good answer as well. Now, we've worked some problems. Let's talk about some properties of the antiderivatives. We have the addition property, which says if you're finding the antiderivative of the sum of two functions, you can find the antiderivative of the first function plus the antiderivative of the second function. For example, antiderivative x to the fourth plus x to the seventh. That's the antiderivative x to the fourth dx plus the antiderivative x to the seventh dx. This is going to be add 1, 5, divide by 5. It gives us this. It's going to have a constant. This, we add 1 to this, gives us 8, divide by 8. We get this. This is going to have a constant. Okay, so now we have 1/5 x to the 5th plus 1/8 x to the 8th. Now we have this constant and this constant. Well, this constant simply means that it doesn't have an x. It's a number, doesn't have an x in it. So when you take a constant and add it to a constant, what do you get? A constant. See, we don't know what C1 is. We just know it's a constant. We don't know what C2 is. So, and we don't know what C1 plus C2 is, except that it's a constant. We don't have to have a C and a C, just one C, okay? We really want you to take the problem from here, say that's x to the 5th over 5. This is x to the 8th over 8 plus c. In other words, this is really all you need to show. Given problem, there's the answer. If you need to show some of this, do, but work towards just being able by inspection to get the answer. We also have what's known as the constant multiplier property. That is, if you have a constant times a function, you can pull the constant out, find the antiderivative function. For example, antiderivative 7 x to the 11th dx, pull the 7 out, x to the 11th, you add 1, makes it 12, over 12 times 7 gives us this, again, just one constant, okay? So, now, we want to address something that we think is important to talk about. The integral of dx is x plus c. Okay, the antiderivative of dx is x plus c. Now, we want to make sure you understand, we're not integrating dx. Okay, we're not integrating dx. We've had a dx in every one of the problems so far, and we're not integrating dx. What are we doing? What gives us the right to say integral of dx is x plus c? Well, here's what's happening. The integral of dx is equal to the integral of 1 dx. In other words, just dx times 1. And 1 is the same thing as x to the 0 power, okay? And add 1 to 0, you get 0 plus 1 divided by the exponent 0 plus 1. And of course, 0 plus 1 is 1 over 1, and x to the first power is x over 1 is x plus c. That's why it's x. You're not integrating dx. This is so important that you understand that. We're integrating 1 dx. Okay, but this is just to show you what's going on. We want, when you see integral of dx, the answer would be x plus c. If we were integrating dy, it would be y plus c. If you're integrating dA, it would be a plus c. I hope that's clear. Now, we have a statement. We have good news. The good news is, when it comes to the antiderivative, there's no product rule or quotient rule. Now for the bad news. When it comes to antiderivative, you have no product rule or quotient rule. Now what's going on here? Well, here's what's going on. When you take a derivative, you can get the answer, be sure to get the answer if you work hard enough at it, enough paper. Some derivatives take a lot of space, okay? But derivatives are possible. Antiderivatives are not necessarily possible, okay? They're not necessarily possible. give you an example, the antiderivative of the sine of x squared, we do not know what it is. Okay, do not know what it is. When you go to more advanced courses in calculus, you will find that you will whole sections of the course will be relegated to finding techniques to obtain antiderivatives. Finding antiderivatives is not necessarily easy and sometimes impossible. So that's why we say it is possible always to find a derivative, not always possible to easily or even find an antiderivative. So we make that statement to wake you up and make you realize what's going on. I guess the reason, the impact is for most students, remembering the quotient rule and the product rule, but in particular, the quotient rule seems to be a problem. And we're trying to say the good news is you don't have that problem with the antiderivative. However, there are other problems that you do have that are greater. Okay, that's all we want to get across there. Here's an example 7. This will tell you whether or not you understand the power rule. The antiderivative of 5x to the 4th, add 1, you get a 5, divide by 5, they cancel, x to the 5th. This is x to the 1/2, add 1 to the 1/2, you get 3/2, divide by 3/2, you get just x to the 3/2. This is x to the -5, you add 1, you get -4, divide by -4, leaves you with plus x to the -4. The integral of 70x is 7x. And this, remember, 7 and pi cubed are both numbers. So obviously the integral of pi cubed dx is pi cubed x plus c. This is thrown into c if you will be distracted and call it pi to the 4th over 4. That's not true, okay? And then, of course, here we have an alternate way of writing this answer. Either of those are good answers. Now, we want to talk about the power rule, which we're still on. This is the only rule we have. We're going to rewrite the power rule. Instead of in terms of x, we're going to do it in terms of u, where u is a function of x. Now, we did this, if you recall, with the derivative. We learned the power rule that was x to the nth, and the derivative was n, x to the n minus 1. But then we found that when you had something such as 2x plus 1 to the 4th power, you couldn't just say 4 times 2x plus 1 cubed. You had to use the chain rule, take the derivative of the quantity. And the same thing applies here with the antiderivative. So just what did we do with the derivative formulas? We rewrote all the derivative formulas after we had gotten through them and rewrote them instead of just in terms of x, but more in a generic u, which took care of the fact that it didn't have to be an x, but that it could be a quantity in terms of x. And the same is true for the antiderivative. So we're going to write the power rule like this. Okay, so we're going to express all the additional ones that we get in this lesson in terms of u. So the integral of u to the n du is u to the n plus 1 over n plus 1 plus c. And this will become, this u will become very obvious in a couple of lessons from now. So if it doesn't make a lot of sense to you why we're doing that, it will very shortly. Now, what's the antiderivative of the sine of u? Well, here's what you do. You ask yourself, what has a derivative equal to the sine of u? Now, if you say cosine of u, you're wrong, because let's check it. The derivative of the cosine is not the sine, it's minus the sine. So it must be that the antiderivative of the sine is negative cosine. So now when you take the derivative, you've got negative, a negative sign, and a negative sign is a sine. Follow me? So you think backwards, you ask yourself, what has a derivative of the sign, cosine, but it's not just cosine, it's minus cosine. Now, on the other hand, rule 3, what has a derivative as cosine? It's the sine, and the derivative of sine is the cosine, so we're done. What has a derivative of e to the u? The derivative of e to the u is e to the u, so the antiderivative of e to the u is e to the u. Now, these are your 4 of your main antiderivative formulas right here in front of you, 4 of them, okay? And you notice how we're really treating it the same way we kind of do with long division. When we go to divide something, we say, what times this gives you this? Okay, we really don't, and we're doing the same thing. We kind of work backwards. We kind of say, ask ourselves, what has a derivative equal to sine? What has a derivative equal to cosine? What has a derivative equal to e to the u? Now, earlier we said there's one exponent you cannot have, and that's -1. And let's see why you cannot have x to the -1 power. Let's look. Let's apply the power rule here. If you add 1 to -1, what do you get? 0. X to the 0. That's no problem. Divide by the new exponent, 0. That is a problem. Dividing by 0, we've got a problem. Cannot have 0 in the denominator, not before and not now. Okay, so what are we going to do? Well, we're going to write u to the -1 as 1 over u du. Now let's think of it if it were in terms of x. X to the -1, okay, next, which is 1 over x. What has a derivative of 1 over x? Now think about the log function. The derivative of ln of x is the derivative of x, which is 1 over itself, 1 over x. So it's the log function. So the integral, when your exponent is -1, it's going to be the integral of u to the -1 du is going to be ln of u. Write it like this, think of it like this, is going to be ln of u plus c. Now, we also put the absolute value brackets around the u. That's because you cannot take the log of a negative number. Okay, you cannot take the log of a negative number. Now, if it turns, you sometimes in a problem and you look up the answer and you see they leave out the absolute value, that's because the quantity cannot be negative. For example, suppose u is x squared plus 1. Well, there's no way that x squared plus 1 is going to be negative. So you really don't need the absolute value symbol there, okay? But maybe to be safe, put it in, okay? Don't overthink the problem. Now, this happens to be, rule 5 is also what I think of as one of the really big, when I say one of the big antiderivatives, it comes up over and over again. So these first 5 are probably the most important, okay? The most important of the early antiderivative forms. But then you need to know them all, because if it turns out that you have to use one of them at any time, then that one becomes important to you. But when you're learning them, and if you're having trouble learning them, work on the first 5 and get those down, and then work on the remaining ones. The rest of these, we're just going to get by asking ourselves, what has a derivative equal to secant squared? Tangent. Derivative of tangent secant squared. So there you have it. What has a derivative of cosecant squared? Well, it's not the cotangent, because the derivative of cotangent is negative cosecant squared, so it's negative cotangent. What has a derivative of secant tangent? It's the secant, because the derivative of secant is secant tangent. What has a derivative of cosecant cotangent? It's not the cosecant, because that's negative cosecant cotangent, so it's negative cosecant. Now, this is one that you may be a little fuzzy on. When the base is something other than e, in other words, e to the u is e to the u, but a to the u, something like 2 to the u. Let's back up and say 2 to the x. The derivative of 2 to the x is 2 to the x times ln of the base, which is 2. 2 to the x ln of 2. Well, remember, we're doing the inverse, which means rather than multiply, we'll be dividing. So the integral of a to the u du is a to the u divided by ln of a. Derivative would be a to the u ln of a, but the antiderivative a to the u divided by ln of a plus c. Let's see how this works. You see, what you're going to do is if you take the derivative of this thing, remember this is a number, the derivative a to the u is a to the u ln of a, and then you've got an ln of a down here, which cancel, which gives you back your original. See, the nice thing about the antiderivative is you can check it. And then we'll just 11, 12, and 13, the derivative of the inverse sine is this. The derivative of the inverse tangent is this. The derivative of the inverse secant is this. Now, there are a number of functions that we are going to need to find the antiderivative of that you don't see here. For example, you don't see the antiderivative of the log. We have the antiderivative that gives you the log, but we don't have the antiderivative of the log. And that's a big important function. You don't have the antiderivative of the tangent. And that's a very important function. So there are a number of them we don't have yet because we aren't ready for them, but we will be soon. And if not in this course, in subsequent courses, okay? Now, we finish with a few tricky examples. These are harder. Well, actually not so much harder, but students seem to get distracted by them or lost. So this is example 8, and we have a number of parts to it. First of all, evaluate this. Now this looks strange. 3 to the x, x cubed, 3 cubed. Well, it's purposely to distract you. 3 to the x. The antiderivative is 3 to the x divided by the ln of 3. This is just 3x squared. Oh, I'm sorry, we can take the derivative. This is simply x to the 4th over 4, okay? Got ahead of myself there, or behind myself. X to the 4th over 4. This is a number, 27. So 27 dx is just 27x plus c. Fairly easy problem. So what's tricky about it? All these threes, you know, you got a 3 here, 3 here, 3 here, and a 3 here. Kind of looks like everything's stacked against you, but it's not. Relax on the problem, okay? That's A. Let's look at B. This is a standard problem, both in the derivative section and in the antiderivative section. Looks difficult, but break this up into 2 fractions. When you do, this becomes x squared. And when you do, this becomes x to the 4th. Subtract exponents. So this is this. So all we're really doing is integrating. We'll substitute this in for this, integrating x squared plus x to the 4th. So that's going to be x cubed over 3, x to the 5th over 5 plus c. Okay. Let's look at c. Here we have x squared plus 2x squared. Now, the only thing you can do with this is square this quantity. Okay, so we square the first term, x to the 4th, multiply the 2 together, which will give you 2x cubed, and double 4x cubed, and square this 4x squared. So this is the same thing as this, and then that gives us x to the 5th over 5, and 4x to the 4th over 4. The 4's cancel, and 4x cubed over 3, and we're done. Now, this problem, if it's instead of being x squared plus 2x squared, if it was x squared plus 2x to the 5th, you would still have to expand the binomial, multiply it out, okay? So we only show you this problem because it's doable as squared, but not doable if the exponent were very large, okay? So this is probably not a problem you're going to likely see unless it is something like squared or maybe as much as cubed. But we thought you ought to see that all antiderivatives are not straightforward some of them require some work, okay? Here's one we want to share with you. E and ln are inverse functions. E and natural log of n are inverse functions, okay? And if you take f inverse of f of x, you get x. Or f of f inverse of x, you get x. You had that earlier. What we have here then, what it turns out to be is that e to the ln of x cubed is x cubed. Now, why? Why? Okay. Well, let's start with y equals e to the ln of x cubed. Let's take the log of each side. The log of y, okay, that's just log of y. The log of this, okay. Now we're going to use the fact that when you take the log of something to a power, the exponent goes in front. So this is going to be ln of x cubed, ln of e. That's all we've done here is use the property. When you take the log of something to a power, it's the power times the log. Now, the log of e is 1, so this is nothing more than ln of y is ln of x cubed times 1, which is just ln of x cubed. Now, look at this. Ln of y equals ln of x cubed means y is x cubed. And that's how we show that this, which is your y, is equal to nothing more than x cubed. So this problem is nothing more than x cubed, integral antiderivative of x cubed, which is x to the fourth over. So if you know this, it's a very simple problem, but it plays off of the fact that this is only true because e and ln are inverses of each other. So basically, e ln of u or whatever is equal to u. Okay, so whatever this is, it's going to be that. Okay, so if this was, say, x squared plus 9, this would be x squared plus 9. So you may want to keep that. And these are just some things, as we said, these were what we call harder problems, but we wanted just to have some things to think about. Actually, if you go through the first 7 problems, they're very doable, and you're really responsible for being able to do those. But now this number 8, which has is a little harder, we want you to ponder that. Let's look at this. This is the last of this question 8. What you have to do here is long division, which you may not have had for quite a while, probably back in simple algebra 1, where you divide this into this standard old long division way. And when you do, we're not going to do the long division. You end up with this. And see, this looks impossible, but this is this, and the antiderivative of 2x is 2x squared over 2, which is x squared, and this is your inverse tangent, and so you're done. So guess what we're saying here is in each of these parts of example 8, you have to step back. They're not automatic. You've got to do some thinking, and we want to encourage you right now, even in this lesson, that even though we want you to be able to do 1 through 7, we also want you to be prepared to do some thinking. Now, if you do not know your derivative formulas, you will probably find the antiderivative formulas somewhat difficult. And I think we're being very nice to say somewhat difficult, next to impossible. You have to know your antiderivative problems. As we said, the antiderivative is to the derivative as long division is to a multiplication. Early in your elementary school, and you learned your multiplication tables, and you knew that 3 times 4 was 12. A little later in your elementary, you got something like this: 3 divided into 12. And usually what you did not learn a table of division. What you did is you ask yourself, what times 3 gives you 12? And that's 4. And that's the same thing we're doing here. When we have the antiderivative of secant squared, we're asking ourselves, what has a derivative equal to secant squared? And it's tangent. Okay. So So you must know your derivative formulas. If if you do, you'll be in good shape. So we conclude this lesson at this point.